Yeah, so this joint work with Lászlo A from London School of Economics and Virginia Williams from Stanford. And we are interested in feedback vertex sets in tournaments. So what have we given as input is a directed graph. So here's a directed graph. And what we want to find is a minimum set S of nodes or vertices whose removal destroys all directed cycles. So we are left with a DAG. And the best, or some approximation algorithm, the best known for this is due to Paul Seymour from 95, where he gives the log n times log n approximation algorithm for this problem in general directed graphs. And the big question that has been open for 20 years now is whether this ratio can be improved or whether there's even a constant factor approximation. So all that's known is APX hardness, but so that leaves a huge gap. And that's why we resort to some special classes of directed graphs, and one particular graph class that has been well studied is tournaments. So a tournament is a directed graph in which there's one arc, exactly one arc between any two nodes. And these tournaments, they play different roles, for instance, in voting theory, or in, you can think of sports leagues, like the soccer leagues where any two teams are playing against each other, and then you put an arc between the two teams depending on who is winning the match. And yeah, the minimum feedback vertex set problem remains NP hard in tournaments. That was proved by Speckmeier a few kilometers from here in '89. And whether or not you believe the unique games conjecture, that you can decide, but still it's at least as hard as vertex cover in general undirected graphs. So the lower bound is 2 on the approximation factor. On the other hand, you can easily get free approximation for this problem because a tournament is acyclic if and only if it does not contain any directed triangles. So one direction is easy, of course, and the other direction you can also give as an exercise to students. So, and therefore, yeah, you easily get a free approximation, and this also holds in the weighted case. Yeah? When you have node weights, then you can also get a factor free approximation, and free hitting set does not have a free minus epsilon approximation, again, assuming the unique games conjecture, so everything seems closed, except that for tournaments, one can do something better. So here's the approximation status or complexity landscape. So if this is the approximation factor, then we know that 1 cannot be achieved if p is not equal to np. And so we are interested in this range between 2 and 3. So 3 is easy. And then in FOCS 98, Kai, Xiaotideng, and Zhang, they showed a 5/2 approximation. So this problem is easier than free hitting set, was likely to be easier than free hitting set in general. And what we show now is that this factor can be improved to 7/3. So how does this algorithm work? This 5/2 approximation, let me first explain that because we are using it, or the similar ideas. So let T5 be the set of 3 tournaments on 5 nodes each that require a minimum feedback vertex set of size 2. So as you can see, there are 3 tournaments here. So because there are some missing arcs here, yeah? So, and you can orient them either way, and you get some isomorphic tournaments. So these 3 tournaments, they have a feedback vertex set of size 2, meaning you need to include at least 2 vertices to hit all the cycles, okay? And what they showed is that if you have a tournament that is T5 free, so which does not contain these 3 tournaments here as subtournament, then you have an integral linear program. So the minimum weight of a feedback vertex set is exactly equal to the maximum value of a fractional directed triangle packing. Yeah, so a directed triangle packing is, of course, always a lower bound on the size of a feedback vertex set. And if you're in a T5 free tournament, they showed that these 2 quantities are exactly the same. And the proof is really very long, and yeah, exploits this to the fullest. So that's That's what they do. And then the 5/2 approximation is quite easy once you have the structural result, because you greedily include all these 5-node tournaments. And yeah, you always include 5 nodes into your approximate feedback vertex set, and you know that the optimum has to include at least 2. Yeah, so you lose a factor of 5/2 in the beginning, and in the remaining T5 free tournaments, you just solve optimally. Yeah, so that's how they do it. And let's see. So if this works for 5/2, how can we do it? Maybe we can even use the same approach to get a 2 approximation. Yeah, that's what we would like to have. And for to see if we can get a 2 approximation, we need to go to the chromatic number of a tournament or of a directed graph. It has been defined, so the chromatic number of a digraph is just the smallest number of partition classes into which you can partition a digraph such that each class induces an acyclic tournament or an acyclic digraph. And in general, you know that, I mean, this should be an equal, so you can always find a partition into at most n log n divided by log n many classes, and this is sharp for random tournaments. So, and Maria Schudnowski and her co-authors, they introduced the notion of a hero. So, and the hero is a tournament H that if you exclude this H, then you have a small chromatic number, namely constant, yeah, depending only on this H. So here's one hero, this hero of Alexandria. And they also introduced another notion, and that's called a celebrity. I think you all know this celebrity. So a celebrity is a tournament that when you exclude it, you have a linear-sized acyclic subtournament, where again, in general, you can only guarantee a logarithmic-sized acyclic subtournament. And clearly, every hero is a celebrity. Yeah? But what they showed is that the tournament is a celebrity if and only if it's a hero. So, and we want to use this for 2 approximation. So first of all, we observe that these 3 tournaments on 5 nodes, they are all heroes. And the constant is, the hero constant is 1/3. Because if you exclude these 5 vertex tournaments, then you can still have triangles and even intersecting triangles. So that's still possible. And now, how can we use this and maybe get a 2 approximation? So the idea would be that we exclude the unique tournament ST6, as it's known in the literature, which consists of 6 nodes, and you need 3 nodes in any minimum feedback vertex set. So it has been characterized that there is a unique such tournament which does not contain a transitive subtournament of order 4, or acyclic subtournament of order 4. So suppose you greedily always include these, you only lose a factor of 2 in the approximation ratio, and then afterwards you use that this tournament is a hero and find this large acyclic subtournament of linear size, and then get a good approximation ratio. But unfortunately, it turns out that this ST6 is not a hero. So even if you exclude the ST6, you can still only, you cannot guarantee anything better than in a random tournament. Yeah, so this approach is not going to work like this. So that's why we do something weaker. Instead of getting a 2 approximation, we settle for a 7-3 approximation. And we remove the 7-node tournaments which need a feedback vertex set of size at least 3. Yeah. Now we want to do again as the people in the 5/2 approximation. So we ask what is the structure of T7 free tournaments. But whereas there were just 3 T5 tournaments, there are 121 isomorphic 7-node tournaments in this T7. And I don't know how many graduate students you can employ on such a task. I don't have that many, so we needed to understand the structure for this. And this we can use to give a 7/3 approximation. So the algorithm is quite simple and also works in a weighted case. So in the first stage, we do iterative rounding, or in the unweighted case, the greedy approach. So we greedily remove all the 7 vertex tournaments in T7. And then in the second stage, we have a combinatorial approximation. So in the 5/2, they had they had a worse ratio here, 5/2, and here in the second stage they were optimal. And we have matching factors in the first and second stage. So how does this iterative rounding work? Well, we write the natural LP relaxation. Since we know that we have to hit only the triangles, we can write this natural LP relaxation where we hit all the triangles with one node and all the T7s with with at least 3 nodes. Yeah, and then we know, so notice that there are no subtournament constraints for T5s. And let's look at an optimal solution X star. So we know that if there's a T7, then because this Q consists of 7 variables, there must be at least one variable which has value at least 3/7. So if we find such a variable, we just include it in our approximate feedback vertex set, so we round it up to 1. And then we resolve the linear program for the reduced instance. And now in the remaining tournament, by what I just said, the remaining tournament, when we cannot find the variable with this value anymore, then this tournament has to be T7 free. Yeah, very easy. And moreover, in this remaining tournament, we have that the weight of an optimal solution X star has to be exactly 1/3 of the weight of all the nodes in this tournament. And that's the second property we will need. So now let's come to this second phase when the iterative rounding doesn't work anymore. Yeah, then we solve this combinatorially. And the main property that we prove is that if I give you a T7 free tournament, then it has a small feedback vertex set. So small means that it contains at most 7/9 of the total weight of all nodes. And this is exactly the ratio that you need because we know that the optimum is exactly 1/3 of all the values. Yeah? And 7/9 times 3 gives exactly this. And yeah, this bound looks very bad. And our conjecture is that this bound is actually 1/2. But even this 7/9 is quite difficult to prove. So what we do is we take our T7 free tournament and we decompose it into layers. And this is also similar to what this Kai Deng and Zhang did. And then what they did, or what we can do with this layering, which I will explain in a moment, is that we can find a small feedback vertex set. And if you have a T5 free tournament, we can efficiently find this. We can efficiently find a feedback vertex set which contains at most 1/3 of the total weight. This is a property that we need to use also. Yeah. So and the idea is that, I mean, as they showed, that the LP polyhedron for T5 free tournaments is integral. And then you just do the LP duality. So how does this layering work? And that's the key property that we do. So, I mean, very natural notation for set S of nodes will be denoted by n minus S set of in neighbors. Yeah, so the set of nodes that have some in neighbor in there. And then we do the layering. So we start with some vertex Z. We pick some arbitrary vertex Z. So this will be our first layer, V1. Yeah? The second layer, V2 of Z, will be all the in neighbors of Z. Okay? And now we always repeat. So the third layer are those vertices which do not belong to the first 2 layers, but which have some which are in-dominated, which have some in-neighbor in the second layer. And then we proceed with the 4th layer, 5th layer, and so on. Yeah? So this is the layering, and we do it, I mean, once we have fixed the vertex Z, everything is determined, and we do it exhaustively until no more vertices remain. Now we say that a pair of nodes, Z1 and Z2, they too in-dominate a set S of nodes if these two, I mean, if every node from the set S either beats Z1 or beats Z2. Okay? And the main combinatorial theorem that we prove is that, well, the second layer, I mean, the first layer, of course, consists of a single vertex, so it's T5 free. Yeah? And the second layer, It's also not too hard to show that it's also T5 free, and of course, since there's only one node in the first layer, it's one in dominated. Yeah? So that's easy. For the third layer, it becomes a bit more tricky, but we can still prove that it's T5 free and is 2 in dominated by the second layer. So that there are 2 nodes in the second layer that are in neighbors of all the nodes in the third layer. And here, of course, we need to use this structure that we have excluded, this 121 7-node tournaments. And now the fourth layer, again, is T5 free, and it's 2 in dominated by the third layer. Now you see the bottom of the slide. So the question is, are all the layers T5 free and 2 in dominated by the preceding layer? And, well, we think, sometimes we think yes, sometimes we think no. So, but even for these third and fourth layers, it's quite an effort to prove that. And if we could prove that for all the layers, then instead of 7/9, we would get 2/3 on the ratio of the size of a minimum feedback vertex X. So it would still not improve the approximation ratio, but yeah, so we could prove it only for the first 5 layers, whereas Kai-Deng and Zheng for T5 free tournaments, they could prove that all the layers are triangle free. Yeah, and we initially thought that we can lift this result. So here's the structure, and how do you prove this? Well, for instance, if you look at the second layer, well, if you know that it is 2 in, or if some layer I is 2 in dominated by the preceding layer, Vi minus 1, then, well, because it's 2 dominated, you cannot have such a structure, yeah? So that's a matching, and, well, this cannot be, that there are 3 nodes that have a matching, so that the arcs go like this. And if you now extend it and think that there would be one more vertex here or one more vertex here, you have to imagine that you will find one tournament from T7. Yeah? So you will find one tournament from T7 which you have already excluded. Okay? So that's the idea behind the proof. So, and now this will give rise to this layering algorithm, and well, we have to do it with a twist. So if we knew that, if we could prove that all the layers are T5 free, then we could just do the layering as I explained. Yeah, you always start from some node of minimum in degree or maximum out degree, put the second layer, third layer, and so on until you're exhaustively done. But then, unfortunately, we don't know if the layers are T5 free, and so we cannot guarantee that in the layers we can solve it optimally. Yeah, that's what we want. We want to use this 5/2 approximation as a black box on every layer, yeah, because every layer should be T5 free, and then get an optimal feedback vertex set on every layer. And now what you could do is, for instance, you could take all the odd layers, yeah, and get half approximation, or all the even layers, depending on which of these 2 quantities is smaller. But since we cannot do this, we have to do this slight twist. So we start with a minimum in degree vertex. And the second layer is also easy. We do all the in neighbors. And now, while there are still some remaining vertices, so let's call this set W, we construct an odd layer, again, as we did before. So we take all the in neighbors of the preceding layer, that's fine. And then we take U prime to be the in neighbors of this odd layer, and the even layer we construct slightly differently. So the even layer, for the even layer, we choose some special vertex Z, and the existence of this vertex is non-trivial to prove, such that the weight of this, the weight of the total number of in neighbors in this presumably next layer is at least the total weight divided by 2. So, and then we have some kind of noise set, so, or some kind of rubbish. So the even layer U2I plus 2 is then only the set of in neighbors of this special vertex and this extra set S. Yeah? So this we have to do to guarantee that all the layers are T5 free. Yeah, so that's why we have to discard something here. And then we go to the next iteration, to the next layer. And in the end, we have three sets. We have the even layers, we have the odd layers, and we have this extra set S. Okay? Now all the even layers will be T5 free, all the odd layers will be T5 free, and we have this rubbish set here. And now we just look. If the weight of the even layers is larger than the weight of the odd layers, then we obtain an optimal feedback vertex set on the even layers and return this set that's just an optimal feedback vertex set of the even layers together with the rubbish, together with everything in the odd layers. Or the other case will happen, namely that the weight on the odd layers is larger, and then we find optimal feedback vertex sets on the odd layers and return it together with the rubbish and all the even layers. Okay? So, and that's already the whole algorithm, and if you analyze it, yeah, then we can prove that every layer is T5 free. There always exists such a vertex. That's, again, I will not explain it now, but it's a bit tricky to prove it. And the important thing is that this rubbish set is small. So it contains at most as much weight as is on the even layers. Okay? That's why we can afford it. Now we can put everything together. So we already said that in the first phase of the iteration, we always have a decrease of at most 7/3 from the integral to the fractional optimum. At the end of phase 1, we are T7 free. We can find this feedback vertex set containing at most 7/9 of the total weight of the whole tournament. And if there are still some triangles remaining, I mean, if no triangles remain, we don't have to do anything. If some triangles remain, we know that the weight of the optimum is exactly 1/3, and yeah, then you do the calculation and you get the 7/3 approximation. Okay. So that's the main result, the 7/3 approximation, improving on the 5/2 approximation. And yeah, the main open problem is, of course, to close the gap from 7/3 to 2. And if you ask me, I mean, my personal belief is that the correct answer is 2. So, and so Anke has shown that there is a 2 approximation for bipartite tournaments. So in bipartite tournaments, you have an orientation of a complete bipartite graph. There, it's trivial to get a 4 approximation, and yeah, 2 is what Anke showed. So I would believe that also in general tournaments, it is possible to get a factor 2 approximation. But for this approach to work, one first has to, I mean, even 9/4 doesn't seem so easy to understand the structure of 9/4 of these T9 free tournaments. I mean, you can also define T9 free tournaments, yeah? But the number of tournaments grows really exponentially, and to understand their structure is quite an effort. Yeah, and if you are not satisfied with this question, there's still the question of the constant factor approximation in general digraphs. And with this open problem, I want to conclude my talk.